In the last video, we did an example of a separable differential equation. In this video, let's just do one more example, hopefully a little bit harder, so that we get a better idea of how we can do these in general. So, okay, I'm going to have to delete twice, it seems. Oh no, 3 times. Alright, perfect. So, let's do, again, the same textbook, question 26 now. As the question numbers get higher, the questions get more difficult, which is good. Question 26 is saying to solve the initial value problem, so it's going to give us an initial condition, the square root of y times dx plus 1 plus x dy equals 0. Now, a very brief side note, whenever you have a differential equation in this form of some function times dx plus some other function times dy, this equation is said to be in differential form. And the reason I bring this up is because in the next maybe few videos, we're going to be talking about the other two analytic methods for solving first-order differential equations, and one of them is called exact equations, and we're going to be using differential form when we're using that. So just wanted to maybe introduce you to that quickly. So, okay, let's get back to the point though. We're solving this differential equation. Well, first of all, it's in differential form, so we want to get it back into the form where we can check if it actually is even separable, which is to say get a derivative and then get hopefully two functions multiplied to each other that are pure functions of x and y. So, let's see how we can do that. We can get our derivative again by dividing by dx. So, we can say let's divide both sides by dx, and we'll be left with the square root of y plus, and now 1 plus x times, alright, good, we have dy dx equals 0. And just as we're doing this, we can quickly get another step done. We can just subtract the square root of y from this. So now we get minus the square root of y. And finally, we can divide by 1 plus x. And what we'll see is that we have dy dx equal to negative square root of y divided by 1 plus x. And now this is clearly a separable differential equation, because on the bottom here we have a function of x, and on the top we have a function of y. And you might say, oh, this is division, not multiplication. But it's important to remember that division is the same as multiplying by 1 divided by your function is your equivalent. So we know for sure that we do have a separable differential equation. Alright, so it's separable. Let's actually solve it. We want to get the dx and the dy on the same side. So let's multiply by the dx and divide by the negative square root of y. We're going to get negative 1 divided by the square root of y dy equals 1 divided by 1 plus x dx. Now, just quickly, let's think about negative 1 over square root of y. What is this going to equal? This should be the same thing as, because the square root of y is y to the 1/2 power, this is going to be negative 1 over y to the power of 1/2. But we know that if you divide by a power, that's the same as multiplying by the negative power. So this should be equivalent to saying that we have, instead of negative 1 divided by the square root of y, we could just rewrite this quickly as negative y to the 1/2 power. Sorry, negative y to the negative 1/2 power, because we're dividing by the square root of y. Now with this, we can just go ahead and take our integrals. So we have the integral of the left side equals the integral of the right side. And for this integral, we can factor out the negative signs. So we get that the integral of y to the negative 1/2 dy, sorry, negative y, negative integral of this over here equals, and then the integral of 1 divided by 1 plus x, this is going to be the natural log of the absolute value of 1 plus x. And there's no inverse chain rule necessary because the derivative over here equals 1. And I suppose we can add our arbitrary constant c on this side and not worry about an arbitrary constant over here, because it's just going to combine with this c and get yet another arbitrary constant. Okay, well, now let's actually evaluate this integral over here. So negative y to the negative 1/2, we know in general, the power rule, we add 1, divide, right? So this is going to be the same thing as negative times, and then this integral is going to be y to the power of negative 1/2 plus 1 is positive 1/2, and we're going to divide by 1/2 again. So I'm going to write that up again. We're going to divide by 1/2, which is the inverse power rule, and this is going to be equal to the natural log of 1, the absolute value of 1 plus x plus c. So now if we multiply this out, 1 divided by 1/2, we can also just rewrite this as 2. So this is negative 2. So we should be able to just divide by negative 2 on both sides. And if we do that, what we'll be getting is y to the power of 1/2 equaling the natural log of the absolute value of 1 plus x divided by negative 2 plus, and we have this c here, but we can just call this c1, c1, and when we divide by negative 2, we can call it a new constant, c2. And finally, because we have this is the square root of y, we can square both sides to get that our y, the solution to the differential equation, is going to be y equals the natural log of 1 plus x, negative natural log of it, divided by 2, plus an arbitrary constant, c sub 2, all squared. And this is going to be our solution. Now, as an exercise of what we were doing in the last few videos with verification, if you want to go ahead and take the derivative of this y with respect to x and see if what you get out is this differential equation, go right ahead. But that is the general method for solving separable differential equations. Sometimes they're a little bit more difficult. Generally, it's because this integral is harder to work out. But in essence, you just get your differentials on the same side as your functions. You integrate, you do some algebra, and you get a solution. Note that sometimes you can't always get it explicit like this, but in some cases you'll be able to get this y in terms of x. In other cases you'll have something strange like the sine of y. I'll just write down the example I'm giving, like the sine of y squared times e to the y to the 99th power or something. You'll get this is equal to like x to the 49th times e to the x or something. And you won't be able to explicitly solve for what y is, but you'll know that implicitly this relationship is true and it solves the differential equation. Something like that. Now, one thing that we have to remember that I think I might have almost just forgotten here is that question 26 is an initial value problem. So not only are we solving for the general solution here, which I have boxed as if it is the answer to our entire question, but we're looking for what the solution to the specific solution is when the initial value y of 0 equals 1. I really should have written this initial value at the start of our problem because I almost forgot about it. So y of 0 equals 1. So let's plug this in. What this means is if y of 0 equals 1, that x equals 0 and y equals 1. So really when x equals 0, y equals 1. So let's plug in x equals 0. Let's plug in y equals 1. Let's see if we can solve this equation. What we're going to be left with is that y is 1. So 1 equals, and I guess I'll switch colors to make it, oops, didn't switch colors, make it a little bit more understandable. 1 equals the negative natural log of the absolute value, x is 0, so this is just going to be of 1, divided by 2. Now, if there's one thing we can remember about the logarithms, the logarithm of 1 with any base, but also with the natural logarithm, that is just going to be 0, so this term goes away. And then we have plus c2 squared. So what we're getting is that c2 squared equals 1, and if we take the square root, we'll then get our conclusion that c2 equals 1. So we can go back into our equation here and substitute for our final answer, that this is going to be y equals negative natural log of the absolute value of 1 plus x divided by 2 plus 1 squared. Well, that is how to solve a separable differential equation initial value problem. And unlike me, you'll probably want to actually remember to do the initial value problem as you're doing the problem. Alright, I'll see you in the next video.